All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.
Hello, good morning everyone. How many of you have heard about different optical instruments like microscope, telescope and the grating? And then have you known anything about that what is the resolving power of those instruments? Can we resolve any of the things with the help of these optical instruments? We'll find it out in detail about the resolving power of that grating, and we'll try to relate it to the earlier topics as well, which we had discussed in terms of the resolving power of different optical instruments. Myself, Professor Nitin Puri. So welcome to Chance Academy. I'll be delivering the lecture on the resolving power of the plane transmission grating. We'll try to relate it to the Rayleigh criteria which we discussed in the earlier lectures. We'll try to find out that how the application of Rayleigh criteria is being applicable to this transmission grating. If you want to go more in detail about these topics, go through the book, and the link of the ebook is available on the screen below in the description box. So now, as we talked about it, that we'll be discussing on the resolving power of, that is resolving power of a plane transmission grating, right? So now let me ask the question in that way. Before going to the resolving power of the grating, normally when we are talking of the grating, it means we are considering number of slits, small slits together. And why I'm saying so in terms of the grating and going in detail about the resolving power of the grating, we must know that we are considering n number of slits together. It means when we are talking of n number of slits, it means small slits, small slits, small slits, small slits, small slits, small slits, so on. And this is number of slits, right? This is number of slits I'm talking of. You see, there are number of slits, number of slits, number of slits, number of slits are there. So when light is incident onto it, light will pass through and will stop at the opaque regions as well. So that particular part, when the light is being stopped with the opaque surfaces, and light will pass through where the small region of the slit is there. So that arrangement is known as that particular grating we are talking of. And normally we do it on the glass. Suppose we use the diamond cutter so that we can put those particular lines, and those lines are very close to each other. So when we say a plus b sine theta is equal to L lambda, which we discussed in the earlier classes as well, that a plus b is known as the grating element. And that grating element is dependent on that how much lines per centimeter are there on that grating. So that a plus b is equal to 2.54 divided by, if it is having 15,000 lines per centimeter, then we must understand what exactly the grating element will be. So it means if any of the glass, if it's cut by cutter, that cutter should be of diamond one. Then we are going to put different lines, and those lines are very close to each other. So when we are saying 15,000 lines per centimeter, it means those lines are very close to each other. But even if those lines are working as if the two lines, there is a space between the two, that will work as a slit, and that part where slit is there, that will work as an opaque surface. You see, so it means we had made an arrangement in a way that light is passing through and light is getting stopped as well. So it means we are talking of opaque surface and the light when it is passing through from that region. So now we could be able to understand what exactly the grating is all about. So when we are talking of the resolving power, what is that resolving power? The resolving power of a grating is defined as ratio of the wavelength lambda of any spectral line to the smallest difference of wavelength d lambda. I repeat it. When I'm talking of the resolving power of the plane transmission grating, we said the resolving power of the grating is defined as the ratio of the wavelength lambda of any spectral line to the smallest difference in the wavelength d lambda. So between this line and a neighboring line, such that the two lines just appear to be resolved, right? This is very important part, I'm making it right now, right? You need to understand it, and I'm saying it again. We know the wavelength lambda, we know the smallest difference between the two is d lambda. So it means one is lambda plus d lambda. Then we are having the difference between the two of d lambda, correct? So it means the resolving power of the grating is defined as the ratio of the wavelength lambda of any spectral line to the smallest difference in wavelength d lambda between this line and the neighboring line, such that the two lines appears to be resolved, right? So what exactly so according to Rayleigh criteria, the resolving power of the grating is equal to lambda upon d lambda. So we got it, lambda upon d lambda, lambda upon d lambda. I'm making this xy. Xy is the grating surface. And Mn is, we are considering this Mn. Mn is a field of view of, suppose, a telescope, right? P1 is now what we are considering, P1 is the primary maximum of a spectral line of wavelength lambda at an angle of diffraction theta n, right? So you see this one, I'm going to make it in that way. This is, suppose P1 I'm talking of, this is, you see this one, suppose this is P2 I'm talking of, right? So this is angle theta n, right? This is, suppose this is a point P where we are getting the central image, right? At point P we are saying we are getting the central image, correct? This is point O, right? Where we are saying that light is incident onto it, right? This is angle theta. Suppose this angle we are saying d theta, correct? And then when we are saying it, we are making it in that way that we are observing like this, and then again with this. If you could be able to see in that way, just look into this one. See, this is lambda, this is lambda plus d lambda, right? So this is m and n, we got it. So this is nth order we are talking of, right? Now, if you see this figure, what exactly, just see onto the screen. XY is the grating surface, as it is clear. Mn is the field of view of the telescope, right? P1 we are talking, P1 is the primary maximum of the spectral line of wavelength lambda at an angle of diffraction theta n. This is P1, right? What is P2? P2 is the nth primary maximum of a second spectral line of wavelength lambda plus d lambda. You see, this is lambda, and this is lambda plus d lambda, right? Now, the angle is theta n plus d theta, right? So it means this lambda is observing at theta n angle. When talking of lambda plus d lambda, it is coming at theta n plus d theta, right? So P1 and P2, what P1 and P2 are? P1 and P2 are the just spectral lines in the nth order, correct? So these two spectral lines, according to Rayleigh, will appear just being resolved when if the position of P2, now you see I'm putting a question mark onto it. I'm putting a question mark onto it and I'm expecting an answer from all of you after going to the break. What exactly I'm expecting it? Will you be able to tell me that how the resolving power is to be explained for the plane transmission grating with the help of Rayleigh criteria? So I'm putting a question onto it. Now what is the condition required that the two wavelengths lambda and lambda plus d lambda will getting resolved? Which criteria is to be followed? I hope you all will be able to know. I am going to give the answer after the break.
मैं दिनेश आहूजा एस चांद एकेडमी से आप लोगों के केमिस्ट्री के जो मुश्किल टॉपिक हैं इनऑर्गेनिक केमिस्ट्री खासकर उन्हें आसान करने आपके पास आ रहा हूं जल्द। तो मेरे वीडियो अगर आपको पसंद आते हैं तो ज़रूर उनको लाइक, सब्सक्राइब और शेयर कीजिएगा।
Welcome to the S Chance Academy. Before going to the break, I talked about it that what is going to happen when in terms of the resolving power of the plane transmission grating is concerned. We considered the two wavelengths lambda and lambda plus d lambda. We observed the two type of pattern where we are getting the central maxima at P1 and P2. Now point is how we are going to say that these two peaks observed from the two wavelengths are getting resolved. Which condition is to be satisfied? I asked this question before the break. Now when I'm telling you right now, the answer is when the Rayleigh criteria is to be followed. So what does it mean? It means the two spectral lines according to the Rayleigh will appear to get just resolved if the position of P2, you see, if the position of P2 also corresponds to the first minimum of P1. You see, P1 is maximum here, minimum here. P2 maximum here, minimum here. You see, if their central maxima is matching or overlapping with the minima of the other, at that particular point of time, we say that Rayleigh criteria is to be resolved. So we can say that if this condition is satisfied, surely we are going to get these two peaks or the two wavelengths lambda and lambda plus d lambda are getting resolved. Now point is the direction of the nth primary maximum for a wavelength lambda is given by the direction of nth primary maximum for a wavelength lambda is given by a plus b. We know that number of times we have done it, sin theta n is equal to n lambda, right? So what does it mean? The direction of nth primary maximum for a wavelength lambda plus d lambda, if I say this is for lambda, and if I say lambda plus d lambda, we can calculate as well what it will be. It will be a plus b sine of theta n plus d theta is equal to n lambda plus d lambda. I hope it is clear to each and every one of you. Why I am saying so? Because you see, if you go to the previous slide, I said it this, when it is for lambda, it is d theta n. When it is for lambda plus d lambda, it is lambda n plus d theta, total angle, theta n plus d theta. And when it is for lambda, it is only theta n, right? So similarly, we have done it here, a plus b sine theta n is equal to n lambda. When it is a plus b sine lambda plus d lambda for theta n plus d theta, we got this equation. So this is equation number 1, this is equation number 2, correct? So these two lines will appear just resolved if the angle of diffraction theta n plus d theta also corresponds to the direction of the first secondary minimum after the nth primary maximum at P1. This is very important. Just see this one, which is the corresponding to the wavelength lambda. So this is when it is possible only. It is possible only when if extra path length is to be introduced. I repeat this part again because it's very important. I'm saying it that the two lines which we are saying it is getting resolved if the angle of diffraction theta plus d theta and plus d theta also corresponds in the direction of the first secondary maximum minimum after the nth primary maximum at P1, right? And what is P1? This is corresponding in the wavelength lambda. So this is possible only when we are introducing the extra path difference of lambda upon n. This is very important, where n is the number of lines on the grating side. Now, capital N is the number of lines on the grating surface, number of lines on the grating surface, right? Number of lines on the grating surface, which is capital N. Now you see what is exactly, now we got it, which is a plus b sine of theta n plus d theta is equal to n lambda plus lambda n upon n. So this lambda upon n, what is lambda upon n? This is the extra path difference. We have introduced it so that we could be able to know that the corresponding, because we want that these two lines to be resolved, and this is only resolved when we are going to introduce this extra path difference, which is equal to lambda upon n. So when it is going to be introduced, so if we are going to equate this previous two equations, if we go to this one, equation number 2 and equation number 3, we could be able to see this one, n lambda plus d lambda is equal to n lambda plus lambda upon n, or n d lambda is equal to lambda upon n, n d lambda lambda upon n, or lambda upon d lambda is equal to n into n. See, lambda upon d lambda is n into n. You see what exactly we got it. When we started this topic of resolving power of a plane transmission grating, we talked of the resolving power of a grating, which is lambda upon d lambda. So when lambda upon d lambda is there, it is coming out to be n into n, small n into capital N. What is small n? What is small n? Small n. And what is capital N? Capital N, we said it. This is number of lines on the grating surface. Small n, we know that. It is of the order we are talking of, right? So the quantity lambda upon d lambda is equal to nn. It is measuring the resolving power of the grating. This is what exactly we have started discussing it. What does it mean? It means that the resolving power of the plane transmission grating is independent of the grating constant. And what is that grating constant? Which is a plus b, which is equal to 2.54 upon capital number upon n, where it is mentioning that how many number of lines per inch or per centimeter are there. Now, so it means the resolving power of a grating is independent of the grating constant, and the resolving power is directly proportional to what? It is directly proportional to the order of the spectrum and total number of lines on the grating. This is very important. So if you see this, why I'm saying so, I'm making this statement again and again, and it means that I'm saying it when lambda upon d lambda is equal to n into capital N. So we are saying it that lambda upon d lambda is equal to small n, which is the resolving power is directly proportional to the order of the spectrum, and it is directly proportional to the total number of lines on the grating surface. So it means for a given grating, I'm going to conclude it in that way. We are trying to understand it, that the distance between the spectral lines is double in the second order spectrum than that of the first order spectrum. I hope you are getting my point. So it means what exactly? So it means this is a conclusion of this one. This is the resolving power of the transmission grating. So lambda upon d lambda is small n into capital N. So what exactly the small n? Small n is that order of the spectrum, capital N is the number of lines on the grating surface, right? So, and the resolving power is lambda upon d lambda. So what is lambda? Lambda is the wavelength of the light which we are using it, and d lambda is the difference between lambda and lambda plus d lambda. And as we have seen in the previous slides as well, that this lambda and d lambda plus d lambda are getting resolved if they are following the Rayleigh criteria. And what is Rayleigh criteria? Rayleigh criteria is saying that if maxima, central maxima is coinciding with the first minima of the other and vice versa as well, at that particular point of time, the two wavelengths which are very close to each other, having a difference between the two d lambda, can be resolved. And we have seen it with this figure and this expressions as well, that lambda upon d lambda, which is the resolving power, is dependent on the order of the spectrum along with the number of lines per centimeter on the grating surface. So I hope it is clear to each and every one of you about the resolving power of the grating instrument of the transmission grating. I hope you had enjoyed the lecture. If you want to go more in detail about these topics, you can go to the S. Chand publishing book, and the ebook, link of the ebook is available onto the screen in the description box. If you have liked this lecture, please like, share and subscribe. Thank you so much.